Hello students, these are the contents from the review lecture 1, part A and part B. So we have seen the concept of frequency modulation and its mathematical expression. We have seen the concept of phase modulation and its mathematical expression. We have seen that FM and PM are inseparable. We also revisited the expression for the bandwidth, which is the Carson's formula, which can be used for the calculation of the bandwidth of wideband FM as well as narrowband FM. We have seen the Bessel's function, which tells us about number of significant sidebands for the calculation of FM bandwidth. Now you have to revise these concepts thoroughly. Before going to the next topic, I would like to mention you that you must be very careful about the unit of the frequency. You have to see that whether it is mentioned in hertz or radian while solving the numericals or deriving the expression for bandwidth. This present lecture is focused on the of FM generation methods. There are the two FM generation methods. One is direct method, another one is indirect method. This indirect method is also called as Armstrong method. Before going into the details of FM generation methods, we should understand the process of pre-emphasis and de-emphasis used in FM transmitter and receiver respectively. We have to understand the stereo signal generation. This is the block diagram for the communication system. Here we have information source, input transducer, transmitter. The signal from the transducer has to pass through different blocks such as filters, modulator, and amplifiers. After the amplification, this modulated signal is transmitted over a channel. In our case, the channel is the air. At a receiver side, the signal is received at antenna and it has to follow different blocks such as RF section, mixer, AF section, and demodulator. After the demodulation, we get our information signal back. In this communication system block diagram, you can see that the noise has been shown at a channel level. This channel noise is an unwanted signal interfering with the desired signal while traveling from transmitter to receiver over a channel, that is air. And most commonly used channel noise is wide Gaussian noise, which has the constant power spectral density, means it affects all channel frequencies equally. This is amplitude interference spectrum of the receiver output. This plot gives us the idea about the effect of interference on different broadcasting systems. So on the x-axis there is a frequency, on y-axis there is an interference, and from the plot we can understand that this interference has constant effect on PM. That means all the frequencies are affected equally in the PM, but the interference effect is linearly increasing with the frequencies for FM system. Means this interference more affects the higher frequencies of FM system. This is important takeaway from this slide. This is the power spectral density of the speech. We know that the frequency range for speech signal is from 0 Hz to 4 kHz. On x-axis there is a frequency and on y-axis there is a power. So from this PSD we can see that the signal power is more concentrated for the frequencies less than 1.2 kHz. The frequencies above 2.1 kHz are weak, hence they have less power. So the frequencies above 2.1 kHz are more affected by the noise, and the lower frequencies. Then what is the solution on this? The solution is to make them strong. The information signal frequencies above 2.1 kHz are boosted before the modulation, and that process is shown in this block diagram. So in this block diagram we can see that the information signal, that is m of t, is provided to the pre-emphasis filter of transfer function hp omega. Now this pre-emphasis filter provides a gain to frequencies from 2.1 kHz to 30 kHz. Now this higher frequency 30 kHz is standard value. For the frequencies less than 2.1 kHz, the gain is 1. So at channel level, these higher frequencies from information signals are not affected by the noise because they have been boosted before the modulation. At a receiver side, after demodulation, the signals from 2.1 kHz to 30 kHz are attenuated to their original level, and this process is called as a de-emphasis. In this way, higher frequencies from information signals are protected from channel interference in FM system. So this is the circuit for a pre-emphasis filter and its frequency response. So these pre-emphasis filters are nothing but the RC circuits. So the input is m of t, that is the information signal, and the output is m of t dash, where the frequencies above 2.1 kHz have been boosted. So these pre-emphasis filters are acting as differentiator. In the frequency response, we can see that the frequencies from omega 1 to omega 2 have been boosted. This is the de-emphasis filter and its frequency response. Again, this is the RC circuit. The input to this de-emphasis filter is m of t dash, which is the output from the demodulator, and the output from this de-emphasis filter is km of t, that is, it is scaled by factor k. So this de-emphasis filter is acting as an integrator. We can see that in the frequency response of the de-emphasis filter. So in this way, the implementation of pre-emphasis filter and de-emphasis filter protects higher frequencies from information signal from the channel interference. Thank you.